Look up. Every star in the night sky is dying. Not eventually. Right now, this second, mid-collapse. And that's the small stuff. The universe itself is running on a stopwatch, and depending on which measurement wins, you get one of four completely different deaths. One is cold and quiet, stretching out for trillions of years until nothing moves. One is a total reversal. The sky itself catches fire as everything falls back inward. One doesn't wait for space to end. It rips space apart, atom by atom. And one doesn't end at all. It just starts over. Today, we're walking through all four, and by the end, you'll know exactly which one scientists are actually betting on. Here's where it all begins. Not with galaxies, but with your coffee. Pour yourself a hot cup of coffee, put it on the table, walk away for an hour. Now it's cold. Room temperature. Notice, it never happens. It never spontaneously heats up again. Heat doesn't reverse. This isn't bad luck. It's a law. Energy always flows from hot to cold, never the other way around, unless something forces it. Scientists call it entropy, but forget the word. Just remember the coffee cup. Heat flows outward until everything settles to the same temperature, and when it does, it's over. No more change. Nothing happens anymore. The cup and the room become indistinguishable. Now walk away. The entire universe is a gigantic, unimaginably large version of that coffee cup. Only instead of a cup, there's space itself. And space has been cooling relentlessly since the Big Bang. Every star that burns, just like your coffee cup, radiates heat outward. And when that heat spreads evenly over trillions of light years, there's no gradient left to do anything with. No engine works without a hot and a cold side. A car engine needs fuel to burn against cold air. Your body needs nutrients to burn against a cooler room. A star is the hot side. Space is the cold side. If you eliminate the difference, you eliminate the possibility of anything happening. No chemistry, no light, no significant movement. Here's the first scenario that comes to mind. A universe where the temperature difference has disappeared, but there's a surprise nobody told you about beforehand. Whether it will actually end that way depends entirely on a number that scientists are still debating. How fast space itself is expanding, and whether that expansion will ever slow down, stop, or reverse entirely. If you miscalculate that number by a tiny margin, you get a completely different doomsday scenario. Push the clock forward, trillions of years forward. Scenario 1. The Big Freeze. Space keeps stretching, forever, faster than light can cross it. Stars burn out one by one, the last red dwarf flickers off around 100 trillion years from now, and after that, it's just black holes, quietly sitting in the dark. Even those eventually evaporate, leaking away as a whisper of radiation over a number so large it barely fits in language. What's left is cold, dark, empty space, stretched flat and silent forever. No stars to wish on, no light to travel anywhere. Scenario 2 flips the script entirely. The Big Crunch. If gravity ever wins the tug of war against expansion, the stretching stops and reverses. Galaxies that have been racing apart for billions of years start racing back together. The night sky, instead of going dark, starts lighting up. More galaxies packed into less space means more light hitting your eyes until the entire sky glows like a furnace door left open. Space itself shrinks toward a single point. Temperatures climb past anything inside a star, and everything, planets, atoms, light itself, gets crushed back into the density it started from 13.8 billion years ago. Scenario 3 is faster and meaner. The Big Rip. This one doesn't wait for stars to burn out. If dark energy, the mysterious force pushing space apart, keeps getting stronger over time instead of staying constant, the stretching eventually outpaces gravity at every single scale. First, galaxies get torn from their clusters, then solar systems get ripped away from their stars, planets flung into freezing darkness. Then planets get pulled apart from their own gravity, and continents unzip from each other. In the final fraction of a second, the stretching wins even at the level of atoms. The bonds holding you together lose the fight, and space tears itself apart down to nothing, everywhere, all at once. And scenario 4 is the strange one, the Big Bounce. What if a crunch isn't really an ending? What if, once everything gets squeezed back into that single point, it doesn't just stop? It rebounds, exploding back outward into a brand new Big Bang, a new universe, new physics, maybe even new laws, cycling forever, over and over, with no first beginning at all. Under this idea, our Big Bang wasn't the beginning. It was just the last bounce, and there will be another one after ours. Here's the part that should genuinely unsettle you. We're not guessing at this from a couch. In 1998, two separate teams of astronomers pointed telescopes at exploding stars, supernovae, that burn with a known, predictable brightness, the same way every time. If the universe's expansion were slowing down like everyone expected, those explosions should have looked brighter than the math predicted. They looked dimmer, further away than they should have been. Space wasn't just expanding, it was speeding up. That single result won a Nobel Prize, and it's the entire reason the Big Rip is even on the table today. Your phone backs this up too. GPS satellites carry atomic clocks accurate to billionths of a second, and engineers constantly correct them for how differently time behaves depending on gravity and motion, the same underlying physics that governs how the whole universe stretches and cools. Meanwhile, space telescopes have mapped the leftover heat from the Big Bang itself, the cosmic microwave background, giving us a direct baby photo of the universe 14 billion years ago to compare against right now. That comparison is how we know the freeze, the crunch, the rip, and the bounce aren't science fiction. They're 4 real answers to one real equation we're still solving. So, which one wins? Honestly, we don't fully know yet. The entire outcome hinges on whether dark energy stays exactly constant, gets weaker, or keeps growing, and our best instruments still can't measure that difference precisely enough over the timescales that matter. New telescopes and satellites are being built right now specifically to pin that number down tighter than ever before. And here's the strange comfort in all of this. Whichever ending is real, it isn't happening on any timescale that touches you, your kids, or your kids' kids a billion times over. The freeze needs quadrillions of years. The rip needs the universe to change its mind about a constant we've barely started measuring. What we do know is that right now, today, the universe is still doing the interesting part: burning, expanding, building galaxies, growing you. See you at the next horizon.